Hi everyone, I'm Mr. Fullerton, and today I want to talk to you about free body diagrams. Free body diagrams are a tool that show all the forces acting on an object and allows you to more easily analyze a physical situation. We'll also talk a little bit about pseudo free body diagrams. If you make a free body diagram and all your forces don't line up with an axis, sometimes if you take one more step and break those forces up into components in what's called a pseudo free body diagram, you can make your life a whole lot easier. So let's take a look at these. To begin with, a free body diagram shows all of the forces that are acting on a single object. The object itself may be drawn as a dot, so you don't need any amazing artwork skills in order to make these diagrams. Further, you start off by choosing the object of interest, drawing it as a dot, and then you're going to draw and label all of the external forces acting on that object. Then sketch a coordinate system, typically choosing the direction of the object's motion as one of the positive axes, and then you're all set to go do your analysis. Let's take an example. Here we have an elephant walking on a tightrope, and apparently our elephant had a bad day and fell off the tightrope. As he's falling, let's draw the free body diagram for our elephant, and we'll neglect air resistance for this problem. Well, to draw our elephant, we start off with a dot. There's our elephant. And what forces act on the elephant as he's falling? Well, of course, we must have the force of gravity on the elephant, and gravity is going to pull the elephant down. And we could write that in several different ways. We could write that as Fg is force of gravity. You'll see some folks write it as capital W for weight, or maybe force of weight. Any of those are acceptable, but my favorite, because I think it really saves you time in the long run, is let's get rid of those and let's write it as mg. The mass of the elephant times the gravitational field strength. If you always write the force of gravity as mg, you'll get away from some later complications and worries about things like, does W stand for weight or work or watts, other things like that. Mg used as the force of gravity on an object. That's the only force acting on our elephant. There's our free body diagram. If we wanted to sketch our axes, we could have our x and y axes, and we're done. Let's take another example. Our poor elephant again falls off the tightrope, but now we're going to include air resistance while the elephant's in the air. Once again, our elephant is a dot. We have the force of gravity, mg, acting on our elephant, down of course, and air resistance is a type of friction. It opposes the motion of an object. So as the elephant is falling down, air resistance must point up. It's actually going to slow the elephant down. So we'll draw another arrow, another vector, and label it FA for air resistance. That easy. Here's another one. We've got a glass of soda sitting on the table. What forces act on the glass of soda? Well, we'll start off by drawing our glass of soda. There's our dot. We have the force of gravity, mg, acting down on our glass of soda. But why doesn't it just go through the table? Well, there must be some other force acting upward that is balancing that force of gravity. We call this the normal force, or capital F sub n. And in some books, you'll see it actually written as just capital N. Doesn't really make a difference. What the normal force is it's a force from the table. As the glass is pushing down on the table bends just a little bit, and it has almost like a spring is pushing back up to balance that. And they call it normal, not because it's not weird or not strange, but normal is a geometry term meaning 90 degrees. Sits this way. The normal to the table must be perpendicular to the surface or up out of the table. That's what they mean by normal. It's always perpendicular or 90 degrees to the surface the object is sitting on. So our free body diagram for our glass of soda sitting on a table. Let's see if we can't apply this to a couple problems. Although these aren't specifically free body diagrams, I think you'll get the idea. Which diagram represents a box in equilibrium? An equilibrium means there is no net force on an object, or all the forces on that object are balanced. Well, if we look for the diagram where everything's balanced, it can't be number one, because we have 5 down but nothing up. It can't be number 2 because we have 2 up and 5 down. That's not balanced. Number 3, we've got 2 up, 2 down, 5 right, and 5 left. That's got to be balanced. 2 newtons up, 2 newtons down gives you a net force of 0 newtons in the vertical direction. 5 newtons right, 5 newtons left gives you a net force of 0 in the horizontal direction. Correct answer must be 2. Or another similar problem, now we've got a box on a ramp, and physicists seem to love objects on ramps. Not quite sure why, but we do. So let's take a look. We've got a block on a ramp. We know the force of gravity, mg, always points down. And because it's sitting on a ramp, a horizontal surface, there must be some normal force perpendicular to that surface, or 90 degrees to the surface. We'll call that normal force. Now, if you look at this situation, the block wants to slide down the ramp, right? Pretty obvious. But if it's not sliding down the ramp, there must be something keeping it from doing so. That must be the force of friction, which always opposes motion. And if the box wants to come down the ramp, the force of friction must be acting up the ramp. Now we can look for which of these diagrams below matches our situation. Well, 2 and 3 don't even have the force of gravity pointing down. And you'll notice here that they're writing the force of gravity as capital F sub W. Means the same thing, but I still recommend writing it as mg. Looks like number 4 has our normal force, our force of friction, and our force of gravity all acting in the directions we've talked about. So that'll be our answer, number 4. Now, there are times when all of the forces that you put on an object don't always line up with the axes you're going to draw. In this case, you can draw a pseudo free body diagram. You break the forces that don't line up with an axis into components that do. Now, if you're in the AP class, when it asks you to draw a free body diagram on a problem, do just the forces first, then make a separate diagram where you break those forces up into components. You'll actually lose points on an AP exam if you only draw the pseudo free body diagram. Let's see what this means. Another box on a ramp problem. If we wanted to draw the free body diagram for this situation, we know we must have weight down, normal force coming out of the ramp. There's some force already pulling it up the ramp, so we must have a force of friction which opposes that down the ramp. So if I were to draw my free body diagram, I'd have a dot, mg down, force coming up the ramp, normal force coming out of the ramp, and the force of friction. And then I would also draw my axes. The axes we line up with the direction of motion. So I would probably call this my positive x, and perpendicular to that, we'll draw our y-axis. But notice that mg doesn't line up with those axes. All right, well, we've got to do something different. We've got to break that component, that weight, into its components that are along the axes. So let's redraw our axes again, and we'll make our pseudo free body diagram over here on the right. So we'll call this plus x and plus y. Now, we still have the normal force. We still have F pulling it up the ramp. We still have the force of friction down the ramp, but that component of gravity, the force of gravity, we need to break up into components along the axes. We can do that by saying this piece of gravity, which we'll call mg parallel, is the component of gravity that's parallel to the direction of travel. And we'll also break that up into mg perpendicular, the component of gravity that's perpendicular to the direction of travel. And you can use geometry and trig to figure out exactly the formulas for these, or after a while you'll probably just remember that mg parallel is mg sine theta, where theta is our angle here, 30 degrees, and mg perpendicular is mg cos theta. So now you have all of your forces, or the components of those forces, lined up along an axis. And that's going to make your life easier when you get into applying Newton's second law, which we'll talk about here shortly. Remember, free body diagrams always show forces, not components of forces. You only see the components of those forces if you make a pseudo free body diagram. So if you're asked for a free body diagram, don't show the components. You can make a separate diagram with the components in a pseudo FBD. Also, as a reminder, never label a force on a diagram as a centripetal force. As you'll learn in the circular motion unit, a centripetal force is any force that pulls an object toward the center of a circle. But there's always something causing that centripetal force, a tension or friction or whatever it happens to be. Don't label forces on free body diagrams centripetal force. Finally, for more help, check out aplusphysics.com. Thanks and have a great day.